All right, so at this point, we want to look at the mean value theorem for integration. And basically, what we're doing is we want to find a value that, a value of x that will actually give us an average value of the antiderivative over a closed interval. Okay? So, just to kind of develop this idea, first of all, what we want to do is, we're not going to, since we just looked at fundamental theorem of calculus, we won't go through all this, but let's say we had the area, the integral from 1 to 4 of 3x squared minus 2x dx equaled 48. Alright, so we'll just accept that rather than doing the work. If we have b minus a, what is b minus a here? 4 minus 1, so 3. Okay? We want to find a value for f of c so that f of c times b minus a will equal the area. Okay? So, if I know that b minus a is 3, I have 3 times f of c equals 48. Okay?
Why do you want to do?
We're developing the mean value theorem here. Okay, so this is what we're trying to do here. So b minus a gives me how wide the interval is. If I were to divide the area by the width of it, I'm going to find a height, right? So basically I'm taking an irregularly shaped object, the area under a curve, and what am I kind of forcing it into? A rectangle, okay? So this f of c equals 16 in this case is saying, okay, I could take all of this area under the curve you can see down here, and I could cut off all of this and squish it into this and make a rectangle out of it, and it would be 3 by 16. Okay? And that height, you could say, of the rectangle is the mean value or average value of the function on the interval from 1 to 4. Okay? Yeah, this is going to give us, if I took all of these different y values, change color so we can see it, all of these different y values and I averaged them, I would get 16. Now it's impossible to do that because there's an infinite number of y values there, but the average of all of them would be 16, we now know. Okay? And again, what we're doing from like a geometric standpoint is we're taking and we're basically squishing this irregular shape into a rectangular shape. Okay?
But are we like really sure like those two shapes they have the same area?
Yeah, they would, because all of this here is going to be the same in both instances. Okay? So what this does is it takes this mess here and reshapes it, and if we squished it together, it would equal this area right here to finish off the rectangle. Okay? So let's look at, this is the idea behind the mean value. This is what we're trying to find. Let's look at the mean value theorem and what it actually says. Okay? If f is continuous on the closed interval from a to b, then there exists a number c in the closed interval from a to b such that the integral from a to b of f of x dx equals f of c times b minus a. And f of c is the average value of f on the interval. Okay? Now notice here, a lot of times what we'll be looking for is not necessarily what f of c is, but where that is. So in other words, what is the number c? Okay? So if I were trying to find f of c, say in the previous example, I would take that function 3x squared minus 2x, and I would say, okay, well, where does that equal 16? Or in other words, I could write it as, hey, I know that 3c squared minus 2c is going to equal 16. Okay, and then I could solve for what c is. All right, 3c squared minus 2c minus 16 equals 0. And then I could work this out. I don't know if that factors or not.
Is it in the 8 and 6?
No.
Hang on, I got it.
4 and 4, 12 minus 4. No, that doesn't work. I don't think this will factor. You'll probably have to use the quadratic formula.
Oh, I thought I got it. Whoops. So that's c minus 2 and 3c plus 8.
3c plus 8 and c minus 2. Plus 8 minus 6. Oh, other way around. But you got the right combo. It would be 3c minus 8
Oh, my bad.
and c plus 2. But that's good, yeah. So, notice it has to be in the interval. So we get two answers here. C is 8/3, which is 2 2/3, or -2. Well, -2 is not between 1 and 4. So C is just going to be 2 2/3. Okay? So that's the value of x that will give us the average value of the function over that interval. Okay? Now, kind of turning this same function around a little bit, if I want to find the average value of the function, I can find the integral and multiply by 1 over b minus a. Notice, from here to here, the average value is simply a modification of that mean value theorem. If I multiply both sides by 1 over b minus a, 1 over b minus a, then I get f of c all by itself. Alright, so that's the mean value which we called f of c originally. Okay? So the formula there is simply the mean value theorem solved for f of c. Okay? So again, it's not a terribly difficult concept to understand here, but do understand that really all we're doing, just to illustrate again, is we would be taking this stuff right here and saying, hey, if we cut it off right there and we shoved it in here, it would finish off a perfect rectangle with a width of b minus a and a height of whatever f of c equals. Okay? Alright. So let's look at an example. Alright? There's a good example of something that changes, but we want to get an average value for, and that is the speed of sound. You know, if you look up the speed of sound, you know, it'll give you an exact number. But the reality is, at different altitudes in the Earth's atmosphere, the sound actually travels at a little bit different rate. Okay? A little bit different speed. The speed of sound, s of x, in meters per second, can be modeled by this piecewise function. The formatting was a little weird, so I highlighted the parts that were the actual function. Then you can see from 0 to 11.5 meters off the ground, the speed of sound is -4x plus 341.
What is that?
X is meters per second, or x is the altitude in kilometers. So up to 11.5 kilometers off the ground.
It's like Mount Everest.
How many miles? It's what is it? 2.2 miles per kilometer.
1.6
1.6
kilometers equals 1 mile.
1.6 kilometers is 1 mile.
1,600 meters on a track is a mile.
I'm absolutely.
Okay.
1.6.
So that's 1.6. 1.6. So
Divided by 1.
11.5 divided by 1.6. Is that right?
It's like Mount Everest.
Yeah.
Yes. It's about 7.5, 8.
Okay. So a few miles up. So basically, most of the stuff that we're going to encounter in real life, we could use that negative 4x plus 341. If we're up in the mountains or up in an airplane or something like that, obviously it's going to change.
I think the formula you mishighlighted.
Does that apply?
Oh man, it got over a little bit. Yeah.
Does that apply inside an airplane?
Well, no, it would not apply if you were up in an airplane and you did something inside the airplane, because the airplane's cabin is pressurized. So the atmosphere is made to be like it is on ground. Otherwise, our ears would. I mean, it's not going to be perfect, but we couldn't handle the altitude as usual. That's why they have to wear like pressurized suits and stuff when they get up high enough and stuff. But anyways, the idea here, okay, is if we can, notice here it says what's the average speed of sound over the interval from 0 to 80. Okay, so up to 80 kilometers off the Earth's surface, what's the average speed of sound? Okay, well, the average we just said was that f of c, and that's going to equal 1 over b minus a times the integral from a to b of f of x dx. Right? So we need to do the integral from 0 to 80 of s of x dx times 1 over b minus a is 80, so 1/80th. Okay? Does that make sense? All right, so if we use the fundamental theorem of calculus, 1 over 80, we're going to be evaluating from 0 to 80 of, we'll use capital S of x for the antiderivative. Right? Okay, so that's 1/80th times capital S of 80 minus capital S of 0. Well, how are we going to find capital S of 80 and capital S of 0?
Plug it in.
Yeah, plug in the interface.
Okay, we've got to find the antiderivative of the parts that we need. Notice here the 3 parts in the middle really don't matter. Okay, we actually showed this on the example we were looking at in the previous lesson, where we took the integral of that absolute value of 2x minus 1, and we said, do we need to cut it up, or can we just go from the beginning to the end? And we saw that we could just go from the beginning to the end. So now I need capital S of x. I don't need it for the middle 3, but I do need it for when x is between 0 and 11.5, and I do need it for when x is between 50 and 80. Okay, so what's the antiderivative of that first portion? Negative 2x squared plus 341x. Okay? And how about for the the part from 50 to 80?
Negative 3 over 4 x squared plus 400 L 4.5 x.
Oop, got my, need to erase a little bit. Negative 404.5 x. Good. And again, that's for x between 50 and 80. Okay? So, if I plug in 80 into that second one, I get negative 3/4 times 80 squared plus 404.5 times 80. Okay. And then I'm going to subtract, the first one was 0 plugged into it. What does that equal?
0.
0. Okay? So negative 3/4 times 80 squared plus 404.5 times 80. Can someone with the calculator help us out on that?
344.5. Oh, no, like the final answer.
Oh, 344.5?
Yes.
What is it before you divide by 80?
2756.
60?
Yep.
Okay. So you divide that by 80 and you get 344.5 meters per second. Okay, so that's the average speed of sound from 0 to 80 kilometers off the Earth's atmosphere, off the Earth's surface.
Doesn't change much though.
Okay.
Probably gonna be 355.
Yeah, I don't know how much of a difference that is between the two. I mean, we could figure it out if you plug in 0, it's 341 right here on the Earth's surface. 341 meters per second on the Earth's surface. If you plug in 80, you'd get, let's see, 40 times negative 3, negative 120, so that'd be 284.5. So it's actually about 80 meters per second slower when you get up to 80 kilometers off the surface of the Earth. So the sound travels slower the thinner the atmosphere is.
Because it travels in matter, that's why it's faster in water.
Huh.
80 kilometers, really high.
Yeah, it is really high.
It's
So, okay. So that's just one application where you have something like this that may vary, that you can find an average for. Still, you could do the same thing, like if you talked about the speed of sound in water at different depths of water, it may go different speed, but you could kind of come up with an average speed of sound in underwater as well. Okay? All right.